Today, we are talking about the laws of nature and nature's lawgiver. So last week I showed a video. The first 15 minutes was on the laws of nature and what they told us about God and, what about miracles and those kind of things. It was just 15 minutes. And so what I want to do is during this hour is I want to expand on that a lot. And so what I would really hope will happen, what I want to do is I want to help you to begin to grasp the wonder and the beauty of the laws of nature. Because when you do that, then that really points to our Creator. So as we learn that, you'll see how the laws of nature point to God and to His infinite wisdom. So I saw this quote the other week, which I thought was pretty interesting. It's from a sociologist by the name of Rodney Stark, and he wrote a book on how the West was won. And so what he said, perhaps the most remarkable aspect of the rise of science is not that early scientists searched for natural laws, confident that they existed, so we talked about that the last couple of weeks, but that they found them. It could thus be said that the proposition that the universe had an intelligent designer is the most fundamental of all scientific theories, and that it has been successfully put to empirical tests again and again. So I thought that was pretty cool. So when you talk about the laws of nature, you get into math a little bit, so this may be your reaction, you get a headache when you talk about math. So let me tell you, first of all, not to be afraid. Number one, I'll be showing some equations. I'll be talking about math, but the important thing is not to understand the equations, but the basic underlying concept, okay? Number two, you know how to add, right? Subtract, multiply, and divide, all right? So you're well on the way. Have you ever made a budget? Okay. If you have, you understand the concept of imaginary numbers. Have you ever gone into debt? Well, then you understand the concept of negative numbers. Now, you understand the concept of a symbol representing a particular number, right? So we could have the letter M, and that could represent mass. If it represents a particular mass, like 3 pounds, and it always represents that, then M is a constant. But if mass could be all sorts of different values, you're not quite sure which, then that's called a variable. So you have variables and you have constants, and they're represented by symbols. So now you understand algebra, okay? Algebra is the mathematics of the manipulations of symbols. So anyway, you're well on your way. But like I say, I'm going to try to explain the underlying concepts, and that's what I would hope that you'll get from it, not the equations themselves. In fact, some of the equations I'll show you, I don't even understand them, okay? So just confession, right? I just understand some of the underlying ideas. So we're going to talk about the laws of nature. Well, where are the laws of nature in the Bible? Well, it starts right with Genesis chapter 1, right? God created the world. He created it by speaking things into existence. So he creates the heavenly bodies, the stars and the moon and the sun, and those are there. They're operating like clockwork. You can imagine the ancients looking up at the sky and they seeing those things proceeding across the sky every night and changing a little bit every night. And so it was like a clock. It was a clock. God made it as a clock for them, because then they would understand when the seasons were coming, when they were going, when it was time to plant. And then God, on the fifth day, God creates the birds and the sea creatures, and it says each according to its kind. We think of human nature. Humans have a particular nature. Each kind of creature has a particular kind of nature. That chair has a kind of nature. Matter has a kind of nature. It just has a way of behaving, right? And so the laws of nature are really the description of how things, of things' nature. So it's a pretty basic concept. It's right there in the Bible. You see this quote from Jeremiah 33. It says, "This is what the Lord says, if you break my covenant with the day and my covenant with the night, so that day and night no longer come at their appointed time, then my covenant with David my servant and my covenant with the Levites who are priests ministering before me can be broken." All right? So he's saying, I made this everlasting covenant with the heavenly bodies. You can always count on the sun coming up, the moon's going to come up, the stars are going to come out, even if, except in Cleveland, So this regularity that God has put into it, well, that's their nature. God created their nature and so forth. So we have this thing called deism. It was a philosophy that came out, I think, partly out of Newton's discoveries of the laws of mechanics, but this idea that nature operates like a clock. So God created all these laws, but it's like a clock. You wind it up and you let it go on its own. And that's what God did, is at the beginning, he created the world, he wound it up, he let it go, but he doesn't involve himself in it since then. So that's deism. Thomas Jefferson was a deist. Benjamin Franklin was a deist. A number of our founding fathers were deists or flirted with it at one time. So anyway, but the Bible doesn't speak of a deism. What the Bible actually talks about God being involved with his creation, even though he's spoken into existence. It goes along with the nature he assigned it. Yet he is also active in those laws as the universe and as the world unfolds. And so you see a lot of poetic language of earthquakes. God makes the mountains quake. Who's doing it? It's God. God is making those earthquakes. He's the one that's making the mountains quake. Or God rides upon the storm or in the clouds. And so it is poetic language, but we do see in Colossians, I actually think it's Hebrew, where it says that the Son upholds all things by his powerful words. So not only did God bring the world in by speaking, he sustains the world by his word, his living word. So God is active in sustaining creation, not just in initiating it, so to speak. And so you see Jesus said, don't worry, look at the flowers. You've never seen anything as beautiful as those flowers. God is the one who gave them their clothing, right? So you see those birds. You don't see them worrying about where they're going to get the next meal because God feeds them. He provides for them. Jesus said the hairs on our head are all numbered. So, the number of hairs on our head is important to God. He knows it all. So I just wanted to mention that just because God created these laws doesn't mean that he isn't active in the universe. God is working through those laws, and he's not bound by those laws either, in which case you have miracles. Okay. All right. So now we get into the fun part. So how can I get you to appreciate mathematics? Well, think of music. So there's a strong correlation between music and mathematics. And this is something that really excited or energized the first mathematicians, who were probably Greek, so Pythagoras, and he noticed that there was this correlation between pleasant chords and fractions. So certain intervals or chords that were pleasant had certain ratios, like in the length of a string. So if you take a string, you pluck it, violin string, you cut it in half, the note goes up by an octave. All right? So, and then you can divide it up into thirds. So you do it in these fractions and you get these discrete notes. So they were fascinated by this correlation between music and mathematics. And so we had this group called the Pythagoreans, which formed, under the philosophy of Pythagoras, and they were a weird bunch, but they basically were really pushing mathematics along. They practically worshiped numbers, and they saw numbers as the basis of all things. So here's a group of Pythagoreans, supposedly worshiping the sun. So back then, in a particular philosophy, it was quasi-religious, right? Even mathematics, could become quasi-religious for folks. So that's what they were doing. But back to this guy. Okay, so you had the whole numbers. So those are also called the natural numbers, and then you have fractions, which we call today rational numbers, and they thought everything was based on these whole numbers and fractions. And then one of their philosophers, a Pythagorean, was able to prove mathematically that the square root of 2 could not be represented by the ratio of two whole numbers. It was devastating. In fact, his fellow philosophers threw him overboard on his ship, supposedly. And there's a lot of different legends about this, but they found this very upsetting. So that guy discovered what we call irrational numbers, which are numbers that cannot be represented by the ratio of two whole numbers. So anyway, so much for worshiping mathematics, okay? All right, so you're probably familiar with Pythagoras' theorem, right? How many of you have you heard? It's hope, right? Yeah. So have you heard of Pythagoras' theorem? Yeah. So you will. Okay. Probably when you get into high school, you're going to probably take geometry. Obviously, you like science, so you probably like math to some degree. So you're probably going to go, take higher math and science in high school. So in high school, you take geometry class, and the whole job is the whole task is proving all these theorems. So you're learning the principles of mathematical proof. So Pythagoras, his theorem says if you have a right triangle, which means there's a right angle between that vertical and horizontal member, then there's a relationship between the lengths of all the sides. So a squared plus b squared is equal to c squared. Pretty simple, but very powerful. You can imagine ancient architects using that. Well, Pythagoras was able to prove mathematically that that was absolutely true. One of the proofs is that little animated GIF file that you see there. So on the right, you see all those triangles, duplicate triangles around a square, all right? So the open area, you can move those triangles around inside of that big square, but the open area is always going to be the same. It may be broken up, it may be moved around, but the total open area is always going to be the same because the area of each triangle is the same, all right? Well, here's what you can do. You have c squared on the right. Now you move things around, and guess what? You get two areas. One is equal to a squared, and the other is equal to b squared. So it's showing that c squared is equal to b squared plus a squared. So that's a mathematical proof. Mathematical proofs are pretty interesting because they're absolute in nature. Once you prove something is mathematically true in this sense, you have proved that it's always true, was always true, is true, and always will be true. So the other thing, though, is what I hope you to see here is that mathematics involves the abstract. It's not the concrete. So the abstract is the realm of concepts and ideas, all right? The concrete is physical stuff, rocks and trees and people and stuff like that. So the mathematical world is an abstract world. So you have points. What is a point, right? It's a thing that has no dimensions. It has no width, no length, no height. Show me a point in this room. Well, you can't. You can point, but you can't show me a point. A line, it's an infinite number of points strung along continuously like that. Okay, so you make it of an infinite number of infinitely small things to stretch those things out. That's the line. Well, show me a line that has only one dimension on it, no width. Okay, right angle. There's no such thing as a perfect. You can't find something that is perfect triangular shape. This triangle you see here is really an abstract concept. So this points to the fact that mathematics is an abstract discipline. But with that abstractness, there's incredible richness. So Pythagoras comes up with this little theorem, a squared plus b squared is c squared, and guess where trigonometry comes from? That's the basis for trigonometry. It's a ratio between those sides. So sine is b over c. All right, so it's not sin. So trigonometry is not sin. It's sine, but we shorten it S-I-N-E, but we take the E off just to shorten it for mathematical reasons. So, and then you have cosine, tangent. So as you get into trigonometry, you'll understand these symbols for these ratios on the triangle. So this idea where you come up with a simple idea and you think you invented it, right? And all of a sudden it has this richness. Points to something that maybe this isn't just human inventions. Maybe they're discoveries as opposed to inventions. There was something there all the time, and we're just beginning to discover it and describe it right now. All right, and guess what? Trigonometry brings us back to music. So sound is the sensation you get when pressure impinges on your eardrum. So a stereo speaker creates pressure waves in the air, and when your ear hears them, it perceives them as music. So this is the description of the pressure for a pure tone. So T is time, so at a particular moment in time. Omega is the frequency or the pitch of the note. It's not exactly that. There's a 2 pi in there someplace, but we won't worry about that. All right, so you take the sine of this angle that's defined by the frequency times the time, and bingo, you multiply it by a scale factor, and that gives you the pressure. So that's the sound. That's a pure tone. So I would hope to see if she can use a tuning fork to make a pure tone and see if you can hear it. Okay. So we use those for tuning. She knows how to use it because she plays violin. And the thing is very precisely machined, so it jiggles back and forth at exactly 440 times a second. 448. Okay. All right, so brought us back to music. Now, what about a violin? How many do you ever get pure tones? Well, you get sort of a pure tone with that, but in reality, a violin has a particular sound to it. It's not just a pitch, but there's a timbre to it. I like to say there's a beauty of it, just like with the human voice, with the trumpet, they all have they can play the same note, but they sound differently because there's overtones in those. There's additional pure tones that are added on top of your main note that you're playing. And that addition of all these other pure tones is what gives the music the tone of a particular instrument, its beauty. And so here you see what if you played a violin, say the 440A on a violin, what the graph might look like. It doesn't look like that nice sine wave, but using the Fourier series, you can break it down into its constituent overtones, which is pretty cool. Use it all the time in engineering. We use it for diagnosing problems with ball bearings. We use it for all sorts of stuff. Musicians use it with their equalizers and all this kind of stuff, but your ear does it. Your ear does this automatically. It does this Fourier series. Your ear can somehow detect those different frequencies and tell you that's a violin, or that's a clarinet, or that's a trumpet, or something like that. So it's just amazing how the human ear can do that. Signal processing, they call it. All right. So I'm hoping this gives you a sense that there's a relationship between music and mathematics, and therefore you might say there can be a beauty in mathematics. All right. So I'm going to give you one more example. Okay. Imaginary numbers. All right. So imaginary numbers for real. Well, what are imaginary numbers? Well, you know what 2 plus 2 is? It's equal to 4. Somebody came along with the idea of negative numbers. By the way, a lot of people didn't believe that negative numbers were really meaningful until I think a couple of hundred years ago. But we use them all the time in accounting and stuff like that. So if 2 times 2 is 4, minus 2 times minus 2 is also equal to 4, and 2 times minus 2 is equal to minus 4. Okay, so what is the square root of 4?
2.
And what else? 2 and minus 2. All right, so the square root of a number, if you multiply the square root by itself, you get the number back. All right. So if I multiply minus 2 times minus 2, I get 4. So you'll find out in algebra that when you take the square root of something, you always have 2 roots to it. All right. What about the square root of minus 4? What the heck is that? I mean, it doesn't seem like it's in any of that list of numbers from plus infinity to minus infinity. But what is it? Does it even exist? Well, somebody decided they would invent. Right? They would invent a number that represents the square root of minus 4. They said I. Let's set I equal to minus 1. All right? So what that means is the square root of minus 4 is equal to I times the square root of 4, which is 2I. Right? But it's made up. Right? Be careful of making up things in mathematics because they have a richness that come along with them. Now we get into complex math. Okay? So this gets into your budgeting, especially the federal budget. Right? You combine a real number and an imaginary number, all right? So this is the federal budget. Okay, so here you see the complex number called 3 plus 2i. So complex number has both a real and an imaginary part. And it turns out it's a very rich field of mathematics. Let me help you understand some of this richness. So we talk about musical beauty. Now we're going to talk about visual beauty. So how can you represent complex numbers on a graph? So here you have the horizontal line, okay? So this is the horizontal line. This is the real part, okay? So this number over here, that's 1. This is a half, this is 0, this is minus half, this is minus 1. Those are real numbers. But this is the imaginary axis. So you multiply everything here by time, I. So I is right there. Minus I is there, I over 2 is there, I over minus 2 is there for a complex number, right? If you go I plus 1, it's actually over here, right? And I minus 1. So that's the basic concept of graphing these complex numbers. So now we talk about something called the Mandelbrot set. Now the Mandelbrot set is a collection of numbers. So we're talking about a collection. So things are either in the collection or they're out of the collection. So how do you determine a number that's in the collection? In this case, you're looking at the number C. So C is a variable. You're going to vary it. Okay, so is C in the black or not? Okay, if it's in the black, it's in the Mandelbrot set. If it's not in the black, it's not. Okay. So what you do is you start with this number Z. So don't worry about that little n, but basically you pick a number Z. It could be a complex, any complex number, and you add C, you add it to C, okay? You take the result and you plug it back in to the equation again, all right?
Square it.
Yeah, yeah, and you square it, okay? So now you take this number, now you take the result, put it back here, square it, add C to it. So it's a recursive calculation, so you just do it over and over. So what happens to Z, okay? Does Z go down to 0 in the long term, or does it shoot off into infinity, all right? If it goes down to 0 or stays constant, it's in the black. If it zips off to infinity, it's out, okay? But what's really cool is you can color things based on how close they are being into the set. So if it's just a little bit outside the border, you can assign a color to it based on how far off it is from, I like to say, converging to a constant. Okay, so now that's all background for this next one. Okay, now enjoy this exploration of the Mandelbrot set.
I'd like to say that you couldn't have made that without the concept of the complex number.
That's right. Yeah, you need the complex number to make that. Somebody invented I. They didn't invent it, they discovered it, right? Because of all this thing that comes out of it. Okay, so we talk about the beauty of mathematics. There's actually a definition of mathematical beauty on the internet. In a sense, beauty is in the eye of the beholder, but actually it's not. I think beauty is there, and the eye of the beholder either has the ability to perceive it or not. So I mentioned before this mathematical Platonism, the belief that mathematical truths are discovered, not invented. They are timeless and eternal. This is what the Greeks determined. And thus it is said, and we'll see there are theologians that say that, therefore, since they're eternal, they exist in the mind of God from eternity. Now, the correlation between abstract mathematics and nature is not necessarily expected. And a number of people talked about that, but it turns out it works quite well. All right, so we're gonna do a little exploration of the laws of physics. So the first are conservation laws. So you have the law of conservation of energy. So what that means is energy cannot be created or destroyed. You have a certain amount, it can flow, it can dissipate, but it never goes away, right? And it's never created. So that's the law of conservation of energy. They use that in Pinewood Derby car racing, right? So what it is you want the fastest car. That means you want the highest kinetic energy. And so the way you do that is you first of all, you try to maximize the amount of potential energy. Potential energy is when you're lifting it up, you're storing potential energy in there, and then you release it like that. So you want to maximize the potential energy. How do you do that? You make it as heavy as you can, right? So that's why in Pinewood Derby races, they said your car can be no more than 6 ounces, and therefore you better make sure your car weighs 6 ounces and no less, okay? The other trick that a lot of people don't know about, they all line up at the nose, all right? So you can increase potential energy by moving the center of gravity aft. So it's still 6 ounces, but you move it back. So if you feel this car, it's weighted toward the back, just enough so it doesn't flip up. Award-winning car. All right. So that's conservation laws. Guess what? You use it to analyze engines. So all these heat engines. And then global warming. Guess what? We have so much energy coming from the sun to Earth, and so much energy that goes out. If more energy comes in than goes out, the world heats up. If less energy comes in than goes out, the world cools off. So the problem is that the energy going out is kind of being blocked or retained by CO2 and other greenhouse gases. So there's several ways to solve that. Number one is you reduce the number of greenhouse gases, right? So that radiation blocked. The other thing is you could block the sunlight going in, all right? So you can throw up dust clouds, volcanoes. Sometimes they'll call global cooling because they throw all this dust up in the air and stuff like that. So another conservation law is the conservation of momentum, right? So momentum is really you take mass times velocity, okay? So that's momentum. The more momentum something has, the harder it is to deflect it, right? So momentum's pretty important. Momentum actually has direction, right? Unlike energy, momentum has direction. And so you have a cue ball coming in at a certain speed. It hits all those other balls. You put the triangle in, and those balls go flying up. Guess what? The momentum of all those balls flying away is equal to the momentum of the cue ball just before it hit it. So that's the conservation of momentum. Now you have the angular momentum, all right? So spin, so a skater, she has to maintain her angular momentum. So if she pulls her arms in, she speeds up because her rotational mass goes down, and that's actually driven by the law of conservation of momentum. So that's why if you pull something in, you spin faster and you pull it out. It's because momentum is related to that distribution of mass going out. So if you pull the mass in, your speed has to increase in order to maintain the momentum. So here's my favorite. It's the ideal rocket equation. This is derived from the law of conservation of momentum. So you have the exhaust velocity, so that has to do with the efficiency of your rocket engine. And then you have the amount of fuel you have on board versus the amount of the rest of the mass. And that's what drives how much of a speed change you can get with your vehicle. So when we're doing space missions, we always talk about different maneuvers in terms of their cost in terms of delta V. So the change in velocity. So you have a certain change of velocity that's required to dock with this. You have so you have all these maneuvers. And so this gets in, it's all determined by how much fuel you have, and you don't want to use up all your fuel before you finish your mission. So pretty simple equation, but this is how we got to the moon. All right, next we get into Newton's laws of motion. So these are pretty basic, but I want you to know, you would think they're intuitive, but actually they weren't. All right, first one, an object remains at rest or going or at a constant speed in the same direction unless a force acts on it from the outside. So this seems pretty basic. It wasn't intuitive. The ancients didn't believe that. They believe if you stop pushing something, if you stop putting your force on something, it would slow down and stop, right? I mean, that's what intuition tells you, but what Newton says, well, actually there's other forces you're not accounting for, and that's the force of friction of the block. So anyway, so the idea, this first law says all the forces, external forces have to balance out to zero if your object isn't going to change in speed or if it isn't going to change in speed. Okay. Now the third law, again, it seems like a law for dummies. This is so trivial. So if you push on something, that thing pushes back at you, right? Well, duh. But this was a conceptual thing, and it enabled certain things. So I use these laws all the time to do analysis. My specialty is structural systems. So we would analyze structures. Like if I push on this, is the car gonna brake? So those kind of things. And so I would use Newton's first and third law all the time. Actually, computer programs did it for me. usually. But we'd end up with, so what you do is you have all these forces, and then you write all these equations that show that with all these forces, they all balance out, so nothing moves. And so you end up with all these simultaneous equations that the computer solved. And when I left, they were up, those simultaneous equations they were solving were up in the millions of independent variables. So anyway, all right. My favorite is Newton's second law, which is force equals mass times acceleration. And what this means is if you know what the force is on an object, this is the net force, then you can, and how much it weighs, you can determine the acceleration. And what calculus does is it enables you from the acceleration to determine what the velocity is and what the position is. So if you know how the force varies with time, you know how acceleration varies with time, and therefore you know how the speed changes with time and how its position changes in time. So basically everything is determined by those initial conditions in the history of the force on it, which is absolutely wild. I think this is one of the things that kind of drove deism. They visit the universe as a bunch of particles that were interacting each other. You know, all these billiard balls, we're all made of billiard balls, and they're all interacting with all these forces. And so if you could figure out the forces of interaction and the mass of all these little billiard balls, you could determine the entire history of the universe, past, present, and future, right? The law of gravity, okay? The law of gravity basically says that the force, the force between two objects is related to their mass and oppositely related to the distance between them. So if you take the one mass and you multiply it times the other mass and you divide by the square of the distance between them, you get the gravitational force. And I talk about the music of the sphere. So gravitational force is the main force that controls the motion of the heavenly bodies, right? The motion of the planets, the motions of the galaxies, of the galaxy clusters. You know, anything flying around in space, its motion is determined by this law of gravity. What's interesting is when you calculate orbits, say if you put a satellite into orbit, you just use this equation right here in those Newton's second law I showed in the previous equation, and you get an orbit, right? So there's 4 different kinds of orbits. That's right. So those orbits are all described by conic section. So conic section is a plane intersecting with a cone. Right. So the path of a satellite going around the Earth is either a circle or an ellipse, or it's a parabola or it's a hyperbola. So we sometimes visualize heavenly bodies as bending a rubber sheet. And you've ever seen those pennies where you flick them and they go spinning around this cone, and it's like they're in orbit around this hole that's in the middle, right? So we kind of envision navigating in space kind of like that. You have all these little holes that you're zipping around, and you're kind of surfing the gravitational field and stuff. And so that's the fun of orbital mechanics. So you put your spacecraft in orbit around the Earth, and then you hit it with your cue ball, and off it goes toward Mars. When it gets to Mars, it's going to fly back. So now you have to hit it with the cue ball again, just the right amount, and it goes into orbit around Mars and so forth. So you're surfing the gravitational field. So I'm hoping you get a sense how much I enjoy this, whether you enjoy it or not. Okay, so now we talk about reference frames. You'll see why in a minute. So reference frame is so to know where something is, you have to always say relative to what? And when something is traveling, you always have to say how fast relative to something. So this gets in the concept of reference frame. So a person on the Earth, he's interested in where things are and how they're traveling relative to him. So he has one reference frame. The rocket that's going on the way up with an astronaut has a different reference frame because he's trying to control his rocket while he's flying. And all this kind of the space station it's going to rendezvous with wants to know where the rocket is relative to him and how fast it's traveling relative to him. Right? So that gets in the concept of reference frames, and that gets in the concept of relativity. Right? What is relativity? So you probably heard everything is relative, right? Morality is relative, Yeah, I mean, but that's what you hear, okay? So, all right, so what we mean by relative is there's no absolute value for position or for velocity. And acceleration, you always have to give it relative to a reference frame. And so in classical mechanics, the laws of physics are always changing. No, they're not. They're unchanging. In any coordinate system, the laws of physics operate the same. So relativity is really saying you have an absolute, and that's the laws of physics, the way things behave, right? As long as your reference frame is an inertial frame, that means it's not accelerating. So what I show here is an experiment you often see called a Foucault pendulum, and what it shows is it shows that Earth really isn't an inertial reference frame because it's rotating. And that rotation is demonstrated by this pendulum walking its way around and knocking down these little supports every day as the Earth spins on its axis. By the way, if the Earth wasn't turning, we wouldn't get weather. So, and also, if it wasn't turning, we'd have to change all our artillery equations. Your satellites wouldn't be able to survey the whole Earth because the Earth isn't rotating underneath them and stuff like that. So, and I've run into Christians who think that the Earth is not spinning on its axis. It's unbelievable, but it's true. Okay. All right. Here at Grace. Okay. All right. So, what is special relativity? So, special relativity is kind of like that what we talked about before. So, the laws of physics are identical in all inertial frames of reference. Right. Talk about what inertial frame. With the addition that the speed of light in a vacuum is a constant, no matter who you are. So the speed of light is not relative to anything, it's absolute constant. And with that, he kind of blew things up, right? So out of his special relativity, you get equals mc squared, right? Which, by the way, is how you get the energy of the stars. Our sun is driven by that equation. The gravity is compressing things together, and as the nuclei of atoms merge together, you get mass turned into energy, and that's what powers the sun. That's what powers all the stars. So if special relativity wasn't true, your sun would have burned out a long time ago. So lastly, we'll get to general relativity. General relativity is kind of generalizing things, and what it's doing is finding a relationship between mass and gravity and space and time. All right. So the theory of general relativity says that the observed gravitational effect between masses results from warping of space-time. It's not a force actually going between objects. It's the fact that this thing called space and time, which are merged together, get warped. So you're kind of showing that analogically there in that picture. Okay. But basically, this curvature in space-time is caused by the presence of mass and energy, and the motion of mass and energy, in turn, is affected by space-time. So what's interesting is the laws of physics and general relativity are the same in all frames of reference, whether they're inertial or not. So here we have this general relativity that sparks all sorts of moral relativity, and in fact, the laws are absolute. So I think that's pretty cool. And by the way, from this equation, you can get that the universe is expanding, and therefore it had a beginning. So I talked about mass curving space, right? Well, here you can see that curvature. So what you have is some cluster of galaxies kind of in the foreground, and then you have these reddish galaxies which are in the background, and the light is coming through that cluster and is being bent because the space is curved around those galaxies by their gravity. And so you can see how these images of all these galaxies in the background are distorted by the curved space, so to speak, around the near field galaxies. Lastly, I said lastly before, but we get into quantum mechanics. So quantum mechanics is pretty bizarre, but I want to point out a couple of things in there. Number one is, see that I? It's the square root of -1. Absolutely essential for quantum mechanics. And without quantum mechanics, you couldn't explain why we have atoms and why we have matter at all, and why we have colors and all this kind of stuff. So that's pretty important theory. That psi, so that's looks like the little pitchfork up there. That's a Greek letter psi. That's called the wave function, right? The wave function, any kind of wave phenomena, can be represented using trigonometry, all right? And the wave function has overtones in it, right? So you have these pure tones in the wave equation, and all these pure tones are superimposed on each other. But when you actually measure it, they all collapse down to a single pure tone. So I think it's kind of interesting. Here's quantum mechanics bringing us back to music again. So, I would say that's philosophical or just a thought that I had over the last week, but I think that was pretty neat. Okay, so now we see this correspondence between mathematics and nature. We can see this beauty in mathematics and the wonder, hopefully a pickup of these laws of nature. So how do you explain that? So you have mathematics, you have nature, you have the human mind that can perceive both. How do you explain that? So this gal, Melissa Travis, calls it the cosmic resonance. So it's this affinity between the mathematics and nature in our minds. How do you explain that? So people wondered about it over the years. So we get to Johannes Kepler. He said, to God, there are in the whole material world material laws, figures, and relationships of special excellency and of the most appropriate order. Those laws are within the grasp of the human mind. God wanted us to recognize them by creating us after his own image so that he could share in his own thoughts. Then you get some more modern folks. So here's Eugene Wigner at the bottom. Theoretical physicist. He said the enormous usefulness of mathematics and natural sciences is something bordering on spooky, the mysterious. There's no rational explanation for it. So he wasn't a believer, okay? Now at the top, Max Planck, one of the founders of quantum theory, he said there is an astonishing resonance between the mathematical laws of nature and human rationality, and he saw a wonderful compatibility between science and Christianity. And I thought that was kind of interesting. Einstein marveled also. He wasn't definitely wasn't a Christian. I would maybe say, if anything, he was an agnostic or a deist. But he saw this compatibility between mathematics and nature as a miracle. We get into this guy, Roger Penrose. He marveled at this too. So he shows the Platonic mathematical world with these abstract concepts, and then he shows us this physical world that reflects some of those abstract concepts. So there's this correspondence between the natural law, the physical world, and this mathematics. But then you have the human mind, which he says is of the natural world, right? You have physical brains and so forth, all sorts of nasty thoughts and stuff. But we can also see that we can perceive the mathematical world, and we can see the correlation with the physical world. And so Penrose, who is definitely not a Christian, said there is an extraordinary concurrence between the workings of the natural world at its most fundamental levels and sophisticated mathematical theory. So how do we explain that? So a naturalist would say, well, humans have invented system of mathematics that simply fit natural phenomena close enough for government work, we like to say, right? There is a lot of approximation, by the way, in engineering and science, because most of these equations you can't solve with calculations exactly. You have to make approximations, all right? But that's not what they're saying there. It's just that it's close enough, all right? Well, the counter argument is that some mathematical systems were developed independently. In other words, and then when the physicist was looking to try to explain things, he says, oh, here's this concept over here, and he applies it, and bingo, it works. So you can't say that he developed the math to fit because it was already developed, and then he saw the application of it later. And secondly, mathematical systems are more like discoveries than inventions. So, all right. The next claim is that the human brain has naturally evolved to carry out advanced mathematical computations. So it was inevitable that as we evolve, we would develop the capability of doing mathematics. Well, the counter argument is that the mental aptitude necessary for advanced mathematics seems far beyond the alleged powers of natural selection. In fact, you might say that those of us who are really good at math and science are probably ill fit for other things like hunting and fighting your own food and stuff like that. It almost seems like they're opposed sometimes. It'd be better if we didn't know so much, okay? And the other thing is that rational thought that is required to know in mathematics must tap into something outside of nature to even be possible. Right? So here's a quote from another agnostic. He says, one of the oddities of human intelligence is that its level of advancement seems like a case of overkill. It is far from clear how such qualities as the ability to do advanced mathematics ever evolved by natural selection. These higher intellectual functions are a world away from survival in the jungle. All right, here's another guy. He is a Christian. John Lennox. He said, "It is not surprising when mathematical theories spun by human minds, created in the image of God's mind, find ready application in a universe whose architect was that same creative mind." So I think I want to end with this passage. Why don't we turn to Proverbs chapter 8. So it says, starting in verse 22, "The Lord brought me forth as the first of his works." Who is he talking about? He's talking about wisdom. So in the book of Proverbs, wisdom is personified as a woman. Right. "So the Lord brought me forth as the first of his works, before his deeds of old. I was formed long ages ago, at the very beginning, when the world came to be. When there was no watery depths, I was given birth. When there were no springs overflowing with water, before the mountains were settled in place, before the hills, I was given birth. Before he made the world or its fields or any of the dust of the earth, I was there when he set the heavens in place. When he marked out the horizon on the face of the deep. When he established the clouds above and fixed securely the fountains of the deep. When he gave the sea its boundary, so the waters would not overstep its command. When he marked out the foundations of the earth, then I was constantly at his side. I was filled with delight day after day, rejoicing always in his presence, rejoicing in his whole world, and delighting in mankind." So I think what we've been talking about today is just a shadow of his wisdom. It's just a small part. When you think of God's wisdom and salvation, his plan from before the beginning of time, the lamb slain before the foundation of the world, and how God was always working. He's, working all things toward his people and toward their salvation and redemption and eternal life. So, this just kind of indicates, gives us a hint of God's wisdom. I saw a definition for God's wisdom once. Wisdom God's wisdom means that he is accomplishing his perfect will in his perfect way. So he has his will that he wants to accomplish, and he knows the perfect way to accomplish it and follows it. So I have on the back of your handout are the words to a song by the Gettys, which is which I love. So you can look it up online, have it played. So, all right, questions, comments. I forgot to see. This is probably partly why I ended early, because part of it is I could see people's eyes closing. So, but also I forgot to show you some things. So, anybody been watching this character?
Yeah,
Yeah, it's a drinking bird. It's a toy you can get. It's a heat engine.
Oh.
It's a heat engine. So where's the energy coming from? It's not a perpetual motion. Every time it hits the water, some energy is dissipated. The friction right here, very little friction, but friction, the drag from the air, it's all sucking energy out of it. Where does the energy come that powers it?
Evaporation.
What?
It's an evaporation.
Yeah, it's actually from the air. So what happens is this has a felt head, and when it gets wet, it absorbs water, okay? So what happens is, as it's waving back and forth, the water evaporates. And when things evaporate, it cools. That's how your body keeps cool. It evaporates sweat, okay? Well, this is sweating, and that's cooling the head, all right? The bottom is warmer than the head, and that causes the fluid pressure to build down here to push the fluid up to the head. Eventually it goes over like that, and the gas leaks through, and then it pops up again. But it's basically, the energy is coming from the air. Now this thing is called Newton's cradle, and what's the fun thing about it? It's just this symmetry. So, us engineers and scientists are easy to please. We like staring at stuff like this for hours, so, But what's interesting is, so if I stop it, okay, and I pull two balls, it's two balls that go rather than one. You actually need both the law of conservation of momentum and the law of conservation of energy together to explain that. Now the problem is things aren't perfectly aligned, and so you'll see it's slowing down, the energy is being dissipated because, I didn't pay enough for this toy off the internet. So, but anyway, I think it's pretty neat. So this is the way we use it in engineering. You use these laws. So both the conservation of energy and the conservation of momentum tells you that when you hit it with one ball here, it has to knock one ball on the other side. If you hit it with two, it goes two. And if you hit it with three, it's actually, three. Anyway, yeah.
Oh, okay. Now, I'm thinking of reference points, but I know there was something else. But when we went over that point with the rocket, the person on Earth, and the satellite, I always wondered about the Wiseman, how right date and the reference point, whatever it was, a star that would that have been their reference frame, that star of Bethlehem?
Well, in a sense, it was. My feeling is the Star of Bethlehem were two things. Right? The first thing was an astronomical event, conjunction between planets, and these wise men probably being astrologers, all right, and knowing about Jewish promises of a Messiah, saw that as a sign that a great king was born, and they went east to see where it was, probably or west, so they probably figured it. But anyway, then I think when they went to Herod, so they followed the star to Jerusalem, right? So that wasn't pointing into Bethlehem, right? I think what happened is after they left Jerusalem, the star appeared again, but this time I think it was maybe angelic. That's what I think. That's my own feeling. Yeah, because it appeared over a house. So I just think God led him there. Angels led him there. That's my feeling. But
There were plenty of angels in that place.
yeah, that's right. Now what's interesting is, so this is fun. So since we have a few minutes, so you have a spacecraft, okay? You have to determine what direction it's pointing. And the way you do that, because you have to do it relative to a reference, it's important because you're going someplace and you know where to point the engine and where to point your instruments, all this kind of stuff. And they have instrumentation on board that can measure the changes in their pointing, right? But what happens is the errors add up eventually and they have to look at the stars to correct their pointing. And so you'll find on all spacecraft, they have star trackers. And so they'll look, and what they do is the thing will automatically, first of all, it lines up with the sun, right? And then it kind of rotates around until it finds a particular star. And then it knows how to correct the orientation of the spacecraft. Now, the way you turn spacecraft is you can use steering rockets, okay? So steering rockets can turn a spacecraft. You just have two rockets pointing in the opposite direction. So that can steer it, but it uses fuel. They also use something called reaction wheels. And what you do is you have this wheel spun up, and what you do is you transfer angular momentum from the wheel to your spacecraft and back again. And by doing that, by transfer of angular momentum from the wheel, between wheels, it can turn the spacecraft and point it. So that's a way of pointing your spacecraft in a particular direction without using fuel. So the space station uses these things called control moment gyros, so big, huge gyroscopes, right? So they have, I don't know, at least 3, maybe 4 gyroscopes, and they're big and they're spinning really fast. And what they do, if they want to turn the space station, this big football field size thing, they push against these gyroscopes that are spinning. And that turns the whole space station around, this big football size thing that weighs ton after ton after ton, using these control moment gyros. And then they go bad, and then you have to send up a mission to replace them. Anyway.
How long do the gyroscopes last?
I don't know. But I know they, I read about telescopes, like I think even on the Hubble Space Telescope, they have gyros. That's how they point it. But every once in a while, those momentum wheels, reaction wheels, they go bad. And so then they have to kind of fudge it. So they have extra wheels, right? If one goes bad, then they use these other wheels.
Tom,
Yeah.
if you take that cup away from the bird, will it still bounce back and forth?
It will until his head dries out. Then
But
his head dries out. Then,
water doesn't cool the beak.
but because there's still water in the head that's evaporating.
It'll still.
Yeah, we'll keep going. He's thirsty. He's frustrated, but he's thirsty. So I had hoped that I could talk about why I believe the Bible is God's word today. But as I got into this, I was afraid that it would take so much time I wasn't going to have time. So I'm going to try to fit it in next week, why I believe the Bible is God's word. Because it's very important. And it all boils down to who is Jesus, right? You know, for me anyway. And who he is, can we trust him, and so forth. So we're going to talk about that, why I believe the Bible is God's word, hopefully next week.
If God could hold the sun for an entire extra day in the book of Joshua, the first chapter, he could do a lot more than that.
Oh yeah.
He extended the whole day in.
Yeah.
Did you know in China at the same time, there's poems and short stories, what happened to the sun, did it fall off? And the cows were waking up and whoever, people would wake up, where was the sun? There's actually, at the same time that was happening, the same thing in the dark side of China.
Poor Moses, he was ignorant. The sun didn't stop, the earth did. You know, it's funny, but you know, it's speaking poetically, right? He's talking about from their reference, you know, they're talking in a reference frame that we all use, the sun stopped in the sky. What a miracle. What an incredible miracle. And you think of how the shadow went back, 10 steps or something like that, and Hezekiah's stairway. It's like, whoa, that's creepy. You know, nobody could do that. Only God could do that. Yeah, but yeah, it's nothing to him. It's nothing. He's spoken into existence, just like when Jesus spoke and the wind and the waves stopped. You know, when he laid his hands on somebody, you know, and healed them, healed their eyes, restored their hearing and their speaking, their muscles, their skeletons. They're absolutely incredible miracles. And he can do it because he's God the Son. He spoke everything into existence. So what he says goes, all right? Except with us, right? So we're the one exception. God can tell us to do something and we don't have to do it because he gives us choice. So Jesus tells the wind and the waves to stop. But he tells the leper that he healed, don't tell anybody else. And what does he do? Word spreads all over the place, you know? So, but God, that's part of the nature God gave us. God gave us this wonderful nature in which we can choose. And so, yeah. But let's pray.